Hello, everybody, and thank you for joining us today. Welcome to today's topic, application of symmetrical components in power system protection. My name is Griffin Cannell, and I'm a digital marketing specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter team. On the left side of your screen, you will see the Ask a Question window. You can submit questions at any time during the presentation, and I will read the questions out during the Q&A segment at the end of the webinar. Additionally, your certificate of attendance, a copy of the presentation, and a link to a recording of this webinar will be sent to all attendees in about 2 business days. Our presenter today is Mike Wilson, Senior Relay Applications Engineer. And to assist with the question and answer session, we also have joining us Abel Gonzalez, Senior Relay Applications Engineer, and Jacob Lloyd, Relay Applications Engineer. With that, I hand things out to our presenter. Thank you for joining us today, Mike.
All right, thanks, Griffin, and thanks, guys, for taking time out of your Friday morning to attend this webinar on the application of symmetrical components and power system protection. Again, I'm Mike Wilson, Senior Relay Applications Engineer here at Megger, and as we go through this, please again feel free to enter your questions, and we will address those the best we can at the end when we have the Q&A session. I will be turning off my camera here at this point because it just to preserve bandwidth. Okay, so starting with our agenda today, we are going to cover first. We're going to cover what is the method of symmetrical components, and as well as some historical information. You know what situation came about that that precipitated deriving this method. It also, because we're dealing with symmetrical components, the symmetrical components is a method of solving solving for quantities on an unbalanced system. We need to know what a balanced system is versus an unbalanced system, and how do these unbalanced systems occur. From that point, we're going to get into sequence components and then using the A operator to come up with like terms. We'll also go into some applications as far as motor protection, transformer, feeder protection, and coordination, and measurement of sequence components. We'll also look at the effects of unbalanced load and faults before we get to our conclusions. And again, we will have our Q&A session at the very end. So first, what is the method of symmetrical components? And this is just to go over a little bit of the history. Back in late 1913, there was Westinghouse was assigned an engineer to form a mathematical study, and this was on the operation of induction motors under unbalanced conditions. And remember, back in this time period, this is in the midst of the Industrial Revolution, very early on in power system in power system electrical motors being used for industrial commercial uses. And what they were noticing that they were having a lot of issues with these motors not performing as expected, or the lifetime of the motor was being severely diminished. And they knew that there was something that correlated with these unbalanced systems. And they're trying to figure out exactly why and how was this happening. And so the electrical engineer that was in charge of overseeing this study, as he was trying to come up with a graphical, he was first looking at a graphical method of solving for these quantities. He started seeing a pattern emerge that it ultimately would provide a segue between a balanced symmetrical system analysis and unbalanced analysis. And of course, this engineer, his name is Charles Legate Fortescue, and and since this study originally it began back in 1913, he ended up ultimately he presented this paper, method of symmetrical coordinates applied to the solution of multi-phase networks. He presented that paper to the AIEE in 1918, and this was to describe how any set of n unbalanced phasors could be expressed as a sum of n symmetrical sets of balanced phasors for values of n that are prime. Now we can't mention and we can't mention Charles Fortescue without mentioning Edith Clark, who Edith Clark later took that paper and she made it more palatable for power systems engineers. She specifically for three phase power systems. And Edith Clark was a first in her field in many ways, as first electrical engineer to be employed in the United States. And by the way, she worked for General Electric. Actually, she worked for General Electric at a couple of different times. She ended up going overseas to work until she was able to come back and be employed as an actual engineer and not as what they called a calculator back then. And then she later went on to become a professor at the University of Texas at Austin. She was also one of the first woman to present a paper at AIEE, and this was she's well known for some of her transmission calculations, and that she simplified the symmetrical component theory. And one second here. One other note to add to this, she was also she patented the first graphical calculator. So first, let's ask ourselves, what is a balanced system? And a balanced system is really you have all phase amplitudes are of equal magnitude. All your phase angles are of equal angular displacement, and this is for a three-phase system. We see 120 degrees apart, so 360 divided by 3, 120 between each phase. But it's most important to remember that it's all phase angles are of equal angular displacement. That's going to matter when we get into the actual sequence components. And of course, if all of your phase amplitudes, if your voltage amplitudes and your current amplitudes are equal, and they're of the phase angles are equidistant, that obviously implies that each phase has equal impedance. And now, as we can see here, we have a phasor representation of a balanced system. We see that our VA is equal to our VB, is equal to our VC. We have its phase angles are equidistant, and we have counterclockwise rotation here. Just another note here. When we speak of a balanced and symmetrical, we're going to use those terms interchangeably. We're going to use those terms. They're synonymous. Balanced versus symmetrical, and unbalanced versus unsymmetrical. And we say unsymmetrical rather than asymmetrical, because asymmetry has to do more with shapes, whereas if something is unsymmetric, it has to deal with quantities. As we see here, our vectors are of equal angular displacement, and of course, all phases have equal impedance. Now, when you have satisfied all these conditions, you can convert this to a per phase equivalent circuit for symmetrical fault analysis. And we can see that here. We see that we have our VAN, our line to neutral voltage, and we've modeled our phase current, our phase impedance, and we have our equations. Basically, after you've evaluated your A phase line to neutral, then evaluating your B phase and your C phase is just a simple matter of adjusting for the for your phase difference. So now what is an unbalanced or an unsymmetrical system? And so basically it's the opposite. If any one of the previous are not true, then you have an unbalanced or an unsymmetrical system. Meaning if any of your phase amplitudes are of unequal, or any of your phase amplitudes are of unequal magnitude, or your angles are of unequal angular displacement, or of course if your phases have unequal impedance, then you will have an unsymmetrical system or unbalanced system. And there's a phasor representation of this. We see that if we assume our VA to be 1 per unit, and we kind of look here at VB, we look at VB and we see that VB is probably about 0.9 per unit. VC is probably around 0.8 per unit. But this satisfies the conditions for an unbalanced or unsymmetrical system. And because of that, a per phase equivalent analysis cannot be used for this condition. So that leads us to asking how do unbalanced systems occur? And when do we see sequence components? We'll get into sequence components here in a moment. But how do unbalanced systems occur? During 3-phase balanced load? No. By definition, the unbalanced system does not occur during a 3-phase balanced load. During a 3-phase, and I would say a 3-phase balanced fault, and no, that also does not cause an unbalanced system. However, a phase-to-phase fault, yes, or a phase-to-ground fault also can also contribute to an unbalanced system. Two-phase or two-line to ground fault, an open pole, such as a blown fuse or just an open conductor. And of course, by definition, an unbalanced load does cause an unbalanced system to occur. So if we can't use per phase equivalent, a per phase equivalent circuit, then what do we do? And this, we get back to Charles Fortescue and his method of symmetrical components. And he proposed that an unsymmetrical in polyphase system could be expressed and evaluated as in symmetrical systems called sequence components. And for a 3-phase system, this means our real-time values, such as our VA, our VB, VC, IA, IB, IC. These are quantities that our relay is monitoring real time. So these are knowns. So if we're just saying, if we take those, we take these known values, and we can create a symmetrical system. We can create 3 symmetrical systems, and this is based on it being a 3-phase system: VA, VB, VC, IA, IB, and IC. And it's in these sequence components will be made up of positive sequence, negative sequence, and zero sequence. And as we see here, we have our positive sequence component, and we see this is all of our systems they all rotate in counterclockwise rotation. And we see our VA passes through the x-axis, then VB, then VC. This is for positive sequence. Negative sequence, very similar. Now, and also keep in mind this. Look at the magnitude here, and this is just relative to the other sequence components. With the negative sequence, we have the same thing. We have a lower magnitude, which means that we do still have overall that counterclockwise rotation occurring. This is just fighting. This is fighting against the positive sequence rotation that we have. Now, if negative sequence were, and we see with the negative sequence, we have our VA and then our VC. So VA passes through the x-axis, then VC passes through, and then VB, which is, so we swapped B and C phases. If the magnitude of this negative sequence was greater than the magnitude of the positive sequence, we would actually have reverse rotation. That motor would rotate the opposite way. And then, like as I mentioned before, one of the definitions of a symmetrical system is that there would be equal angular displacement between each phase. And as we can see here, with our zero sequence component, we don't have 120 degrees because this is all together. We don't have 120 degrees, but we still maintain equal angular displacement because we have an angular displacement of 0 degrees. 0 degrees between VAO to VBO to VCO to VAO again. So now let's look at the math here, and we see the equations down here, and that's simply this is just the mathematical representation of the graphics that we just showed. Our VA is equal to VA1, which is our positive sequence, plus VA2, our negative sequence, plus VAO, which is our zero sequence, and so on. VB and VC. You see our VA, our positive sequence components coming in, and followed by our negative sequence, VA2, VB2, VC2, followed by our zero sequence components. And so this is, vectorially, we're just, all we're doing is we're adding these tail to head. Each component. Now, what's the advantage of this? The advantage of this is that now we have 3 systems. This can be solved. This could be solved as per phase equivalent. So now but the problem here, and I'm going to just step back here 1 second. The problem with this is that our VA, VB, and VC. Now we have 3. The VA, the VB, and the VC. These are known values because we're monitoring this with either our bus or our line PTs. But these are real-time quantities that the relay sees. And I need to cycle through here just real quick. However, we have 3 equations and we have 9 unknowns. So it's important for us to be able to, if we could somehow put VB and VC into VA terms, into like terms, we could possibly solve this. If we had 3 unknowns and 3 equations, we can use linear transformations to solve this. And so this is why we come up with the A operator. And just a quick note here, the A operator is in polar format. It's just 1 times 1 angle 120, and this allows us to go from VA to VB, to define VA or VB in terms of VA, because we know what the phase shift is, or define VC in terms of VA, etc. And if you look at this a little bit closer here, if 1 plus A, which is 1 angle 0, plus A, which is 1 angle 120, plus 1 angle 240, of course, these vectorially sum to 0. So starting off with our equation, our VA equals VA1 plus VA2 over plus VA0, we're going to look at we're going to assume that our VA1, VA2, and VA0, that we're going to put everything into those terms. So when we drop down to VB and we look at VB1, using that A operator, we're going to go A squared times VA1, which is basically 1 times 1 angle 240 times A1, and we see our VA1 equals it's VB1 equals VA1 angle 240. And likewise with our negative sequence component, see that our VB2 is VA2 angle 120. And remember, with the negative sequence component, this is going to be opposite of the positive sequence. So if you look at the phasor representation of it, our VB2 and VC2 are going to swap places. And finally, VA0 is equal to VB0 and VC0. Remember, this is a symmetrical system, so all the magnitudes are equal. And because our angular displacement is 0 degrees between each phase for the zero sequence component, the zero sequence component for each phase is equal to one another. And we'll do likewise with VC. Just defining VC, first the positive sequence component of VC in terms of VA, or VA1, the positive sequence component of VA1, and the negative sequence component, and the zero sequence component. Which leaves us with the following equation. Now that we've put these all into terms of we have our knowns, our VA, VB, and VC, and then we've put everything else in terms of our sequence, our VA sequence components. This allows us to use transformations to solve this in a matrix format. As we see here, we have a linear transformation, and then reverse transformation. And then this leaves us finally with our sequence equations. And we've been working with the voltages. However, this also applies to the currents as well. We see our I0, I1, I2 equals and one second. Okay, here we go. There's a slight lag here. Okay, so just to summarize what we covered a little bit earlier, and we were asking ourselves what causes these unbalanced load or fault conditions, and these are just the more common conditions that can exist on a system. And of course, we have our three-phase balanced load, and we're looking at what sequence components are present. Now, even during a balance, so there's always going to be sequence components present. On a purely balanced system, if that does indeed exist, which usually doesn't, you're going to have positive sequence. positive sequence. That's on a balanced system. You're not going to have negative or zero sequence. On a three-phase balanced fault, you're also going to have you're going to see all positive sequence, no negative or zero. When we get into the phase-to-phase faults, we see positive sequence and negative sequence, but no zero sequence. We have no path to ground. And with single line to ground faults, then we introduce the zero. With single line to ground faults, double line to ground faults, open poles and unbalanced loads, of course, then we begin to see the zero sequence component come in. And so for those conditions, single line to ground, double line to ground, open pole and unbalanced, we see all three sequence components. So now let's look at application of symmetrical components in protection. So how do we first with detecting the sequence components on an unbalanced system? First, we got to ask ourselves, what are our known values? And like I said earlier, it's our VA, VB, and VC, and IA, IB, and IC. These are the quantities that are coming in from our CTs and PTs that are on the system. They're our real-time values. And historically, how were these measured? How were electromechanical relays capable of measuring these quantities in order to provide system protection? Well, there's a number of ways, which we're going to see here in a moment. But with negative sequence, we've always had an issue with being able to analyze this without numerical. Numerically, we can do that. Otherwise, we have to use a lot of clever designs, clever wiring to achieve that. And so, yeah, even though the method of symmetrical components it's been around for well over a century, and the effects of these sequence components on equipment, it's very well documented. The detection and measurement of these quantities hasn't been that easy. Electromechanical relays, they can measure imbalance as ground current traveling on the neutral, the secondary of the neutral of the secondary current circuit. However, the negative sequence components, they required implementing a lot more complex filters. But with the zero sequence quantities, now again, when we see ZSQ, PSQ, ZSQ, and NSQ, that's going to stand for our positive sequence quantities, negative sequence quantities, and zero sequence quantities. And likewise with PSCs, NSCs, and ZSCs, that's going to be for currents, positive sequence currents, negative sequence currents, and zero sequence currents. But with zero sequence quantities, they did not require complicated wiring schemes. With your zero sequence current, you typically bring all your returns together. Your imbalance shows up on your neutral, and that the sum of these phase currents are proportional to the zero sequence quantity. At that point, that neutral can be fed into a relay for measurement, as opposed to the negative sequence quantity filters, which required a lot more complicated design schemes. And and because of these design schemes, the components for making the filter are more costly. And again, the more parts you have, the more points of failure you could have, and of course the higher cost. Now, of course, going from electromechanical into solid state relays, they, even though we were able to, it was a huge advance forward, because we no longer needed a warehouse to accommodate all the protection relays for a substation. It was we saved a lot of space, a lot of real estate with the solid state relays. However, you still didn't have the ability to perform a numerical analysis and to find the magnitudes to measure these negative sequence quantities. So you still had to implement a rather complex filter design. But with the advent of digital and digital/microprocessor numerical relays by the likes of George Rockefeller and Edmund Schweitzer, the ability to perform the numerical calculations were greatly simplified. They greatly simplified this process. And George Rockefeller, he was one of the first. He actually developed the first computer-based or numerical protective relay, and that was commissioned at Pacific Gas and Electric's 230 kV Tesla substation. And I think this was back in roughly 1968, 1969. And that stayed in service after it was commissioned. It stayed in service for 6 years. And then, of course, we had Edmund O. Schweitzer, who invented the first commercially available microprocessor relay right around 1977, I believe. In the early 80s, companies such as ABB, Areva, and SEL, they were the early pioneers. They were pioneers in the early market in the early 1980s, and they made huge strides in technology. They all contributed to early advances in numerical relay, numerical/digital/microprocessor relay development. And again, by the mid 90s, right around 1995, these digital relays, microprocessor relays, were being commissioned in most new transmission and generation sites. And this is just a slide that shows some of the microprocessor based relays that you commonly find. Now, of course, with these microprocessor relays, not all of them offer negative sequence overcurrent protection, but many do, and many offer the negative sequence overcurrent element to detect phase-to-phase faults, phase reversal, single phasing, which is like an open conductor, and as well as heavy motor unbalance. So, by now we're well informed that the presence of zero sequence, positive sequence components, that occurs in a balanced system, and it doesn't necessarily contribute to, that's built into the design specifications of the equipment. And I think we're well informed now that the presence of zero and negative sequence components is an indication of abnormal conditions on the system. And what happens if we ignore it? Well, if we ignore it, of course, we're going to have the same issues that they had back in 1913. When Fortescue originally performed that mathematical study for Westinghouse. But these components, these unbalances, these sequence components, they will show up as damage in your equipment. At first, just detecting it, it's easy to detect because it's an unbalanced load. You can detect that through your basic metering and phase currents. You have your knowns are your VA, VB, VC, IA, IB, IC. Your instrument transformers will tell you that. You can see that easily that it's an unbalanced system. However, prolonged operation under imbalanced conditions that will cause rotor heating, and we're talking specifically about motor protection here, and then and this will end up propagating itself as excessive torque forces and rotor heating, which damages the components and eventually manifests itself as machine vibration. So let's just take a look at what positive sequence current does in rotating equipment, and we can see that positive sequence current it generates a counterclockwise rotating magnetic field. This is assuming ABC rotation, and for the purpose of this webinar, we are going to assume counterclockwise ABC rotation. That's going to be our norm. So the positive sequence currents, they generate a counterclockwise rotating magnetic field at synchronous speed. And now the synchronous speed is determined by the system frequency and number of poles. Now it also, for a motor, the rotor rotates at slightly slower speed than synchronous. And this difference is called slip. Now this slip is proportional to the current flow that's induced in the rotor bars, and also ultimately the mechanical torque that's available. And as we can see here with the flux with the rotor, and let me bring up my here with our flux around the motor. We see our counterclockwise rotation and our stator. But as opposed to our negative sequence current, now with the negative sequence current, again, negative sequence current, we're looking at now we're looking at a force that's opposing that positive sequence. So instead of having that ABC rotation, we're looking at ACB rotation, and we can see that that negative sequence, based on if the system rotation or system sequence is ABC counterclockwise, the negative sequence currents, they generate a clockwise rotating magnetic field, and that opposes the rotation of the rotor flux. And because the current induced in the rotor is proportional to the slip frequency, the stator currents induce voltages that are 2 times the synchronous frequency. That are almost 2 times the synchronous frequency. And that's also that leads. We're going to see that our negative sequence elements are more sensitive to phase-to-phase and phase-to-phase ground faults than typical phase overcurrent protection is. And if we look over here, we see that the flux, the rotor, we have our counterclockwise rotation, but our stator, the negative sequence component, it is opposite of that rotor, of the rotor flux. Now, how do we use these sequence components? Well, with microprocessor relays, we use them in several different ways. We, microprocessor relays, they use the sequence components for calculating heat source, and this is just a model of a thermal model of a motor, and it's used to calculate the heat source for that motor, and because we evaluate this under 2 different states. We evaluate it under a locked rotor state versus a running state. So each of those models each state is modeled separately, and then it's ultimately summed. And we can take a look over here at some of the characteristics of current and torque and versus slip. Also, sequence components are used for generator I squared T alarm and trip characteristics. Now, when it comes to testing, I brought up some of the some screenshots of some settings here from a popular relay manufacturer. It's when it comes to testing, it's really important to review the settings, and one of the biggest difficulties that testing technicians face is and this is not just with symmetrical components, but across the board, is understanding what is being tested, what's being tested, and it can be as simple as understanding what units are we using. Are we using per unit? Are we using a percentage? Are we using secondary values versus primary values? But if you get a chance, you should review the settings and understand the coordination between the elements. If it's possible, if you work on a system, if you're dedicated to a specific utility or industrial complex, you get a feel for what their expectations are, what their settings are, what their standards are. And so if you're privy to seeing what the upstream and downstream, how this is coordinated upstream and downstream, then by all means take advantage of that. I know that it's often taught that as a test technician, you should just test whatever settings you're issued. But what I think gets mistaken here is that you, as a test technician, you should not take the liberty of making changes to the settings. I think that's the big thing, is that you shouldn't take the liberty of making changes to the settings, but you should always have a questioning attitude. You should always have a questioning attitude when it comes to testing, because there's countless times that I've been in the field that you see something, and again, if you're familiar with a system that is standardized, you begin to pick up on you can easily see inconsistencies. So whenever you see that kind of inconsistency, that should automatically catch your attention, and you should at least go back to the protection engineer and verify that this agrees with the intent of the protection scheme. Also, compare your settings with the nameplate info. Nameplate info of the device, whether it's a transformer or a motor or whatever device you want to. If you can compare that, if there's anything on the nameplate that pertains to your settings, make that comparison. Make that physically compare what's on that nameplate out in the field to what your settings are, and going along with that mentality, cross-reference your drawings. Make sure that your drawings agree with your settings. And that's some of the things. CT PT ratios, whether you have a delta PT connection versus a YPT connection, and CT connections, etc. Your system voltage, all of these. And I bring this up. I know it sounds very sounds very basic, but these are all things that commonly come up in the field that you occasionally will find a discrepancy between your drawings or your nameplate information and what you find in a settings file. And it happens enough. It's not just an anomaly. It happens enough that it's worth always looking at, always verifying. And lastly here, well, not lastly, just another tip is that you understand how these settings fields are set up, how they're defined. And I'm just going to take take a look over here, and if we look at the maximum phase time overcurrent here, we have 4.9, and this is an amps secondary. This is what we typically we typically expect. However, if we look over at some of these others, I'm not sure if this will show up, but a phase overcurrent, and this right here is for a cell 710. We see our 50P1P phase overcurrent trip pickup at 7.38. Well, this is very easy for a technician to take a look at this setting and say, okay, well, I'm gonna put I'm gonna expect a pickup at right around 7.5 amps, 7.3, 7.4 amps. However, that's not the case. This is actually a multiple of the full load amps. So whenever you take that into account, now I come back over here and I look at my full load amps. I have 400. This is now you have to account for all of that. And if you don't, if you just rush in and you start testing, and you're going to get it's not going to pick up. You're not going to get the results that you're expecting. And it's important to be able to understand why, because you're out in the field. You're usually on a time crunch, and it's just important to really thoroughly get into those settings and really understand what you're testing. If at all possible, set up your tests beforehand. Look at the setting and know what to expect. And also, and this gets me very, very often, because we get into a groove, and we're assuming that the torque control or whatever is supervising that element is always going to be one, and that's not the case. It very often is not the case. And so when you're testing and you're not getting the pickup, you're looking at your sequential events recorder, where you have your SCR set up specifically for certain elements. You're not seeing those assert. Take a look at your torque control. Take a look at whatever is in series, whatever element or condition is in series with that element that you're trying to test. Because if you're not satisfying that condition, if you could easily satisfy it, then by all means do that. Through the use of a pre-fault or just maybe it's an LOP condition that needs to be removed before that element is enabled, and try to accommodate for that. If at worst case scenario, maybe making that change and documenting the change, also documenting that in your records, saying that, hey, I this was there was a 32 element that was supervising this element that I'm testing, and I wasn't able to satisfy that condition, so I changed it. I enabled it with I redefined it as one, but then went back and changed it later. But it's very important to document any kind of document how you test these elements. Also, now there's also conditions where some utilities they don't want you to overwrite trip outputs, and maybe you can get around that by using spare outputs on the relay. But there's often they want you to test on that trip output, so it's important to understand where does that how are those elements, how do those elements coordinate with each other? There's usually a small a small range, where a small current range or voltage range where you can assert that element specifically. Be aware of that. If you have if you're privy to that, to those type of basis documents, then by all means, take advantage of all your resources. And of course, we do like to. It makes it much easier to be able to isolate an element, which is why I bring up testing on a spare output, especially if you're troubleshooting. Testing on using a spare output and just isolating that single element to test. And this is just an example of one of the something I covered a couple of slides ago, as far as the 50P1P element that's in one of the 710 relays, and we see that we had a secondary value of, or we had a value of 7.38, but that was a multiple of full load amps. So 7.38 times the full load amps, with our full load amps being 400 amps. Now with our when we looked at our CTR or CT ratios, we saw that was a 120 to 1. So when we calculate this out, we see that it's looking at 2,952 amps, almost 3,000 amps primary. And when you divide that 3,000 amps by 120 for the CT ratio, you come up with 24.6 amps, or 2,952 amps divided by 120. We get our 24.6 amps as a secondary value. This is the value that you're going to use. You're going to push in order to. This is the amount. The 24.6 amps is what you're going to inject in order to. It should be your expected value for to verify that 50P1P pickup. Again, with this element, if it was a 50P1T element, if this was an element that had a built-in had a time delay built into it, let's just say that the time delay was built in at 1 second, and if you're not able to isolate that, then you can get a little creative with your testing methodology. You may need to adjust the pulse width whenever you're testing. Adjust your pulse width for that instantaneous element, and to get that element to come in. Now we're going to quickly take a look at how symmetrical components are used in transformer differential protection, and again, this is very it's a very high level, but we often use with the digital protection relays, it gives us the ability to remove zero sequence currents from the relay inputs, and this is due to during a through fault condition, the CTs they may saturate, and when they saturate, that you're gonna see your imbalances. That's going to show up. Say if it's on a delta Y transformer, you're going to see zero sequence currents. You're going to see zero sequence currents on the Y side. However, they're going to propagate to the delta side as a zero sequence current that is trapped in that delta winding. And because of your secondary current wiring, you're going to see that zero sequence on one side, but you're not going to see it on the other side. You're not going to see it on the secondary wiring side from the delta side, and this could contribute to a false operation or misoperation of that 87 element. Now, if you have a through fault condition, and it's very common with the utility companies, if you assert an 87 element. If you trip on differential on that transformer, this is going to greatly extend the time that it's going to take to bring that transformer back into service. Very often that there's a protocol, there's procedure protocols for this that consist of testing that transformer, retesting that transformer to make sure that there are no no abnormalities exist. And simply because transformer is often that's the most expensive component in the substation, besides your employees, of course. Now, traditionally, this was in order to remove this. This was with electromechanical relays. You connected your CTs on the delta side of the transformer. You connected those in a Y configuration, and then on the Y side of the transformer, you connected your CTs in a delta configuration. And not only did this remove the zero sequence quantity, but it also compensated for that phase shift, because for that that 30-degree phase shift between the delta and the Y. Now, with numerical relays, we can leave everything connected. We can leave our CTs connected Y or delta. We can with a numerical relay, we don't have to come up with a lot of different clever wiring schemes to accomplish this. We can use compensation factors, and then, as you can see here, with our this is compensation factor. This is for a single 30-degree phase shift, and we can see that whenever we're calculating this current, that we're subtracting our IA or IB from IA, and then for our IB, it's IB minus IC and IC minus IA. Now, with all of these terms, we can see that the common term, the term that's common between each value, between each phase current, is that we have an identical zero sequence current. So whenever we subtract one phase from the other phase, we're going to have all these terms here, but our zero sequence is going to directly cancel out, which in effect it cancels out our zero sequence. And one second here. Okay. And this is just some of the other compensation matrices for phase shift and zero sequence current elimination. Just a note, whenever a CTC of 0 is simply an identity matrix, but for non-zero values, we can see our matrices here, and and these for non-zero values, it does remove the zero sequence component from the measured current. So, summarizing the transformer protection, we know the microprocessor-based relays now use compensation matrices to accommodate the phase shift as well as filter zero sequence currents. And each transformation, it accounts for a 30 degrees phase shift from 0 degrees. And each non-zero transformation removes the zero sequence currents from that relay input. So lastly, in summary, the method of symmetrical components, it allows us to calculate sequence components for more sensitive detection of system faults and abnormalities. For a technician, understanding what these components are and how to test them, it greatly improves the efficiency. It makes it much easier to test these elements out in the field. Again, it's just very important to understand what you're testing, and if you have the opportunity to if you have the opportunity to let's say experiment with bench test relays, it would definitely behoove you to do that, to be able to look at some of the characteristics of what you're doing. How, if you could break it up into symmetrical components, see what that increase in current, what that 1 amp increase in current does, from going from balanced to unbalanced, and how that shows up in your symmetrical component calculation. And there is a plethora of resources available out there online, as well as publications through IEEE, that expand on the use of the symmetrical components in many different fields of protection. I know today we've only covered just a very, very small amount of how symmetrical components are used in power system protection, but there is a gob of stuff out there, and over the past 20 years, it's really come full circle. Just looking over some of my old books, my power system books from college, and this is roughly 20 years ago, to date myself here, but looking back on that, there was a lot of excerpts that I saw there. It was like, negative sequence components can be used for this or be used for that. Maybe it's used in Europe, but in the U.S. at that time, it was still greatly not used. It has changed quite a bit over the past couple of decades. And so that leads us now to our questions. And I'll hand this back over to Griffin.
All righty. Awesome. Well, thank you so much, Mike. At this time, the presentation portion of the webinar is officially concluded. We will now take some time to answer as many of your questions as possible. Again, if you have any questions, please submit them into the Ask a Question window on the left-hand side of your screen. For those of you that are leaving, please be sure to fill out our survey before you head out. We'd greatly appreciate it if you could take a couple of minutes to provide your feedback, so that way we can improve on our future webinars. On the survey, there's also a field where you can request a demo or quote for any Megger products if you're interested. Again, a copy of this presentation, your certificate of attendance, and a link to a video recording of this webinar will be emailed to everybody in about 2 business days. The link that you used to join this webinar can be used to view the recording of this webinar in about a couple hours after we wrap up here. You can view video recordings of our previous webinars, as well as register for upcoming webinars on our website at us.megger.com/webinars. Be sure to register for our next webinar on June 28th, titled Streamlining Protection and Control Testing Processes Using the PMM2 Power Multimeter. And that'll be presented by Jacob Lloyd, who is our panelist today. Alrighty, so now let's get to some of your questions. Our first question here is going to be for Abel. They ask, I've heard that triple harmonics behave like zero sequence. Why is that?
Hi, can you guys
yeah, we can hear you.
Yeah, okay, thanks. Well, the reason is relatively. This is an interesting question, and I get it from a lot of people, because not everyone that deals with harmonics deals with negative sequence and positive, and in general symmetrical components, because a lot of people that do that, they're more of the electronic side, and they don't deal with the power system side of this kind of thing. And the thing that makes them similar is that they both have the zero sequence components that you saw from Mike's presentation. They all have the same phase angle. If we see the okay, let me see how can I do this. Just a second here. Boom. Do you see the screen there where we have the zero sequence, negative sequence, and positive sequence component? Can you tell me that, guys? You do see is that
Yes. Yeah, we see
being
it.
present?
Okay.
Yes,
Okay,
we can
so
see it.
the zero sequence elements, what they have is that the phase angle of the three components, the three phase components, is the same, right? Now, when you have a triple harmonic or any harmonic, really, you have to realize that the phase angle of the harmonic is multiplied by the harmonic number, right? By the harmonic index. So, in particular, for the triple harmonics, when you have a phase angle of, for example, for phase B, you have a phase angle of 120. That means 3 times 120, that's 360, which puts the, let's say, phase B harmonic in phase with the phase A harmonic, right? Because 360 is the same as 0. And the same goes for phase C, because in phase C you have 3 times 240. That's actually 2 times 360, so it's just 2 turns, and again, you are on the same phase angle as phase A. So for a triple harmonic, you have, and I'm only going with 3, but you could do the same for 6, 9, really any harmonic with an order of 3. You come up with the same math that phases A, B, and C, the 3 are in phase, right? And what that means is that they end up circulating through the neutral if there is any, because when you sum these 3, they come up with an amount through the neutral that is 3 times one of them, because when you sum 3 things that are in phase, well, it's just basically putting one next to the other, and that's why they say that triple order harmonics behave like a zero sequence component. Okay, that was the answer, I guess.
Oh, sorry. I keep forgetting that my mic is muted. Thank you so much, Abel. Our next question here is for Jacob. They ask, I've tested negative sequence pickups before, and they seem to pick up well before expected. Why is that?
So first thing, you can hear me, correct, Griffin?
Yep, we can hear you.
Perfect. All right, so you have to look at relay to relay how the element is actually measuring and responding to negative sequence, because it's not always going to be set in just pure I2. And for reference, right, we talked about it earlier, we drive it back, when we talk about I2, we're talking negative sequence. You're going to see I2 often in your settings and everything you're doing. And so depending on how it is if it's an electromechanical relay, if it's a digital relay, how it's able to take that measurement and how it's able to respond to it, a lot of times it's going to be set as like 3 times I2 is what the setting is going to be, or you might see it as, as a percent I2. So how much negative sequence is there as a percentage of the primary current, the primary system current, right? The I1, the normal system currents. So it's not always going to be set in just pure I2 equals this, and then I trip. So it's very important, just like anything with a relay, right? Go to your relay manuals, make sure you know how is it being measured, how is that setting actually set, and make sure, is it a multiple of I2? Is it a percent of I1 in I2? So that you understand when you're doing that testing and when you're applying those settings, what it's going to actually respond to. If I need to, I can probably expand upon that further, but I think that's all I've got for the moment.
Excellent. Thank you, Jacob. Abel, we're going back to you for this next question. They ask, why do zero sequence components circulate through the neutral? Abel, we still got you here?
Muted myself between questions. I shouldn't have done that.
No worries. I did the same thing.
I was talking to myself. Well, what I was saying is that I kind of gave that answer in the previous reply, and the reason is that since they have the same phase angle, right? what ends up happening is that the sum of the three equals 3 of, because when you have, let's say, a balanced system, the sum of the three is 0. So there's nothing going through the neutral. In an unbalanced system, whatever unbalance you have goes through the neutral. In the case of the 0 sequence components, they all have the same phase angle. So the sum of the three equals 3 of one of them, and that goes through the neutral. I see in the Q&A a comment that's very valid that says that the delta filters out triple harmonics. And that refers to my my previous question. Since they behave like 0 sequence components, well, it stands to reason that they're also filtered by the delta, which means that they remain circulating inside of the delta, which doesn't mean that they are not present on the other side, right? If they're produced on the Y side and there is a neutral, they will circulate through that neutral. And what ends up happening is that the transformer will provide, ampere balance. So if the triple harmonics are on the Y side, they will be present inside of the delta. So you have the ampere balance for the transformer winding, but they won't show on the line right outside of the delta. So that comment, whoever made it, is a very valid and very good comment. Okay.
Fantastic, thank you. It looks like our next question is for you yet again. They ask, as a rule of thumb, what is a recommended percentage of negative sequence protection versus TOC 51 protection for feeders protections?
Well,
maybe you can expand upon that.
Yeah, that is a kind of a tough question to answer. And that depends on the application of the feeder. However, what I have seen is somewhere around 5% of negative sequence to positive sequence. You want to keep your negative and 0 sequence elements very, very tight, which doesn't mean that I'm saying that the 0 sequence should be kept at 5%. That's different because 0 sequence is related to neutral protection. And so it's a different, different considerations there. Neutral and ground, right? Protection. But in the case of the negative sequence component, if the feeder feeds mainly motors, you have to be very concerned with whatever amount of negative sequence you have there, because of whatever Mike explained in the presentation, where he showed the effects of negative sequence components on induction motors. And in particular for motors, the recommendation for the voltage imbalance is around something below 5%. And I have also seen that something like that applies for the ratio of the 51Q, or negative sequence protection, to the positive sequence protection. Okay.
Thank you so much, Abel. Our next question, we're going to Jacob, and it asks, why is negative sequence polarization used over 0 sequence polarization?
So, keep in mind that when we talk about the polarizing quantity for a relay, right, whether it's directional, whatever it is, it's a quantity that establishes and lets us then talk about directionality in the circuit. So when we look at that, through that lens, and we talk about negative sequence, positive sequence, 0 sequence. So you're gonna, especially in T&D applications, transmission line applications, your negative sequence components are going to tend to be larger than your 0 sequence components. They're going to be more usable as that polarizing quantity. So you need to have enough there to use it for that polarizing quantity. So it's just a matter of the relative magnitudes of each of those sequence components in the system.
Awesome. Thank you so much, Jacob. Our next question is back to Abel. It asks, why is it that a small voltage imbalance can produce such great damage in an induction motor's rotor?
Well, Mike was, yeah, can you hear me? Yes. Mike, I kind of answered that in his slides. Where is that? Positive? No, not this one. I guess it would be this one here, where he presented. Well, the thing is that if we go to the previous slide in the presentation, we see that the current that circulates through the rotor in an ideal voltage system, the current that circulates through the rotor is directly proportional to the slip. And the slip, remember, is basically an expression of the difference between the synchronous speed of the voltage system, which, for example, for a two-pole motor at 60 hertz, that's 3,600 RPM, and the difference between that synchronous speed and the speed of the rotor, which could be somewhere, I don't know, 3550 or something. So the point is that typically in an induction motor in operation, that slip is a very small number. Whether you express it on percentage, or you express it in hertz, or you express it in RPMs, it's going to be a very small number. When we are talking about the slip, as it refers to the positive sequence component. But what happens is that when you have a negative sequence, now we are talking about a voltage system that is producing a magnetic field, or more accurately, the the maximum of a magnetic field that's rotating against in the direction opposite to the rotor at the same 3,600 RPM. So and that those 3,600 RPM, of course, refer to the frame, right? So when we're talking about that negative sequence system, we're now talking about a slip that's almost twice the synchronous speed. So whereas before we were talking about a very small number, if we're talking in percentage, it could be 1, 2, 3% or something like that. Now we are talking something that is 200%, right? So what I'm trying to say is, in the other case, the full voltage was producing a very small current that was, well, not very small current, because the currents tend to be relatively large, because the voltage induced on the rotor divided by the very small resistance that you have in the rotor gives you enough current to produce torque. But then you have a current that is being produced by a voltage that is producing a magnetic field that's rotating at almost twice the. So you have a very small voltage, which is the voltage of the negative sequence, but now that voltage is moving way faster relative to the rotor of the motor, and so it tends to produce a relatively large amount of current, which will tend to, or will manifest in counter torques, rotation, vibration, overheating of the rotor. Remember that there's a lot of heat being produced that's directly proportional to the square of the current that's being produced by the negative sequence component as well. And that's why you don't want to have a negative sequence voltage that is very large, which means you don't want to have a very large imbalance in the system that powers up induction motors. Okay.
Thank you so much, Abel. Mike, it looks like we're going to you for this next question. It asks, can there be negative sequence current in a balanced fault?
Okay, thanks, Griffin. And answer to that is yes. It's now, by definition, a balanced fault, a three-phase balanced fault. Technically, it shouldn't. However, real world, even if your source voltage, your source voltage is balanced, the the line is still the line still can present some asymmetrical characteristics. So your three phases, they may have some slightly different impedances, and so that's going to account for some very, some small and often what we would consider like negligible negative sequence currents and voltages during a balanced three-phase fault. Another thing that can contribute to this, that even though that we have it's a three-phase balanced fault on the system, our bottleneck is really how are we detecting this? How are we bringing this data in? And that's through our instrument transformers. This is through our CTs and our PTs, and these CTs and PTs there is a standard tolerance that's associated with each of those with those, but there is still a built-in percentage of error that's going to occur. So whether that be through saturation of a CT, or how CTs saturate different from one another, that can show up as an imbalance, unless you have that true linear relationship between your primary, your secondary, your actual values. You definitely will show some imbalances, and those imbalances do show up as negative sequence and or zero sequence components. Hopefully that answers your question on that.
Thank you so much, Mike. Jacob, we're going to you for this next question. It asks, why are zero sequence and negative sequence settings generally more sensitive than positive sequence settings?
So the way to think about it is sort of, if you, like Mike said, right, there's zero sequence and negative sequence components that can exist in a properly operating system, because it's not a textbook, right? There's the reality of the system that's out there that can develop. But even then, relative to your actual, primary system, your I1, the real system, they should be pretty vanishingly small until something goes wrong. And so what that lets you do is you can set protection elements using those quantities at very, very low magnitudes compared to the system magnitude, the positive system quantities, that now you can respond to that fault or that issue developing before it gets out of control, before it becomes a catastrophic failure. And you can sort of think about that if you're out in the field, right? Think about it like the way you can use a ground or neutral overcurrent element versus a phase overcurrent element, where the magnitudes can be much, much smaller to protect you, because, hey, those things should never be very large in my healthy running system. And so that's really just what it boils down to, is that, hey, we might have some, but they should always be very, very small in that healthy system. So it lets us respond before we have catastrophic failures, which is always what we want from our protection, right? We want to catch it early, not smoke and fire time.
Jacob. Alrighty, it looks like our last question here is for Abel. It asks, I've seen imbalance defined in terms of sequence components. How is that different from the traditional way of defining imbalance?
Traditionally, imbalance is defined by doing a very simple math, using simply the magnitudes of the, let's say, voltages or currents. What you do is you average the voltages on the three phases. You find the maximum difference between one of the voltages and that average, and you divide that by the average. That's one way of doing it. That gives you a number directly from the magnitude that you have in the system, and it's very simple. It's a very effective way of calculating imbalance. Now, when you have access to the calculations of the sequence components, then you can define two measures of imbalance. One of them could be the ratio of the negative sequence to positive sequence component, and the other is the ratio of the zero sequence to the positive sequence component, which is used in some. It's not starting. It's been used for a while already, along with the traditional way of measuring imbalance in protection applications, and in particular in power quality. This has become the favorite way of evaluating imbalance. I mean, using the sequence component way of calculating imbalance, but this means that you have to have access to the calculations of the zero sequence and negative sequence component and of course also to the positive sequence component, which makes it a little bit harder to implement. But numerical, in particular, microprocessor relays have made that something that's run of the mill these days.
Alrighty. Well, thank you so much, Abel. It looks like we're out of questions today. To everybody in the audience right now, if you think of anything else, please do not hesitate to contact us offline. We'll be more than happy to get back to you. As a reminder, a copy of the presentation, a certificate of attendance, and a link to a video recording of this webinar will be emailed to all attendees in about 2 business days. Thank you all for attending. After we conclude here, please remember to fill out our survey. That survey will include a field for you to let us know how we did and to request a quote or a demo if you're interested. And again, I'd like to thank you all for attending and have a great weekend.